Hey there and welcome to another LeetCode problem. So we're going to continue with the random problem challenge today. And let's get started. We have a medium problem, so let's see if we got something new or not. Find the right interval. Okay. Looks like we never did this. Okay, cool. You're given an array of intervals where intervals start to end. Okay, so intervals standard. Each start is unique. Okay, the right interval is an interval j. Okay, so let's start writing this down. So given array of intervals where intervals I equals start I and I, and each start is unique. Okay, so that's pretty straightforward. The right interval for an interval I is an interval j such that start j is greater than or equal to end I. Okay, and start j is minimized. Okay, so if we have some interval like this, I'm guessing, then the start, if that's I, the start of j would want to be something like 2 something. Right, we want to minimize the start of j. Okay, straightforward. Note that I may equal j. Okay. Okay, so that's interesting. So I may equal j. Return an array of right interval indices for each interval j I. Okay. If no right interval exists for interval I, then put -1 at index I. Okay, so let's look at the examples. So I guess for j, there's only like one value, but let's take a look. Okay, so 1, 2. There's only one interval, so it outputs -1. Okay. Okay. So I thought, okay, the starts are unique. Okay. There is no start interval for 3, 4. There's no right interval, okay? The right interval for 2, 3 is 3, 4. Okay. Okay, that makes sense. And the right interval for 1, 2 is 2, 3. Okay. So first of all, I mean, I can already see that this is one thing. We're going to want to sort. For all these intervals, you generally want to sort because you want to actually have them in the right order. So let's keep going in these examples. So the right interval for 1, 2 is 2, 3. Okay. Now we have this 1, 4, 2, 3, 3, 4. Okay. There is no right interval for 1, 4. Okay. And 3, 4. Okay. The right interval for 2, 3. Yeah, right, because, yeah, sure. The right interval for 2, 3 is 3, 4. Since 3. Okay. Okay. So really what they're asking is, what is the smallest starting point for the next interval? Can be the same. Yeah, it's for the next interval. Now, do these intervals, let's see, I interval length 1, I interval I length is 2. Start less than or equal to. Okay, so the other thing is a start can technically equal to an end, so you can technically have an interval like this as well, which is interesting. Note that I may equal j. Yeah. And so that would be one thing, I think, is if you have, I think if you have an interval like this, then the j for that one is just going to be this as well, I think. Okay. So really what we want is we want the smallest start value after, right? We want the smallest start value. Yeah. Okay, I think I'm starting to get it. I think this looks like a stack, but let's just make sure. Is that what we want? Yeah. Yeah. Okay. And then yeah. Okay. So okay, I think I'm starting to see it. I just want to make sure. So we do want to sort. I think. Do we want to sort actually? Do we need to sort? That's the question. We might not. We might just need a stack. 3, 4. Yeah, actually, I'm going to hold back on the sort. No. Wait. Yeah, we do need to sort. But we need to do something else. So the problem is sort makes us lose the order of these, and we actually do need the order of these. So I think what we actually want to do is for each interval, maybe we can add another value like index. So let's do that, and then we can sort. Sounds good to me, I think. Right? So let's just see what that looks like. So we just say for in range length intervals. Let's actually add an index, then we can sort. Because we want to know where the indices started out, I think. So that's just going to be intervals I dot append I. Now we can sort them. Now we can sort. By the way, once again, I didn't actually record how long we're going, but so far we're at 8 minutes. Okay, let's do that. Now let's print intervals and see if that should be what we want, though. I mean, it's probably not the best idea to actually print these, but that's okay. So 1, 2 is 2, 2, 3, 1. Yeah. Okay. So each start is unique. I don't know if that even matters. Sure, let's just say it does. Okay. Okay, so now we got what we wanted. Now everything is sorted. Right? Yeah. Okay, so now what we need to do is we need to have a res. So let's just do that. So res equals -1 times length intervals. Okay, so that's going to be our result array. They're all going to be -1. So now I think what we need to do is, now that we're sorted, what we need to do is we need to have a stack, I believe. And then what we need to do, yes. Okay, so I think I kind of get how this algorithm works. So what we're gonna do is for each element, like for example, let's just go through this 3, 4, 2, 3, 1. So I think let's just go through that and let's see what that would look like really quick. So that's gonna be 1, 2. That's gonna be index 2. Then we have 2, 3. No. Yeah. 2, 3, index 1. And then 3, 4, index 0. Okay. So what we're going to want to do is we're going to go through like each interval one at a time. And then if the start and the end is the same, so if it's like this, then the next, so it does say that I may equal j, And so if the two numbers are the same, then the next biggest value for this is this, because they can be the same, right? So the result here would just be 1 if they're the exact same. But if they're not, so let's say they're not here. So let's just go, we have this 1, 2. And we basically, what our algorithm is going to do is and we also have a stack. So let's just have a stack here. What we're going to do is we need to figure out what we actually need to push on the stack. But what we need to say is if there is something on the stack, and as long as this start index is greater than whatever's on the stack, then the next value of whatever's on the stack is this. Right? So that right now there's an empty stack. And then what we need to put on the stack is the end index and the actual index, like the index of where it is in the interval. So that's going to be, the end index is 2, and then it is 2, so these are the two values we want. Okay. And so now that we have that, let's go through the rest of it. So for right now, we have nothing. Now we have this 2, 3, 1. And so 2, 3, 1. So we're going to do the same thing. We're going to see, and let's just have a res as well, by the way. So res is going to be -1, -1, -1 for now. Okay. So we take this 2, 3, 1, and we say, okay, we do have a stack. Now, as long as this value is greater than or equal to whatever is at the end of the stack, which is this, is that actually going to work? Now that I'm thinking about it, I do see a problem with that implementation. And the problem with that implementation is that, yeah. So I do see a problem with that implementation. So the problem would be something like if this is like 1, 9, or actually if this was like 1, 2, and then this was like, whatever, 1, 2, 2, and this was, let's say, 3. Actually, this would be like 1, 9, 3, 4. And this would be like, and not 3, 4. Actually, would we ever have a problem that way? I think we would. Yeah, I think we definitely would. Yeah, we definitely would. Because there might be some stuff here that is bigger than some stuff here. But if it's bigger or smaller, what if it's smaller? Yeah. So if this is like 1, 2, actually, no, if this is smaller, so the right value has to be, I don't think it is a problem. The right value has to be, like, if this is smaller than this, then I think it also has to be smaller than this. Yeah, because, yeah, so that would just be popped off. So if this is smaller, like if this 2 is smaller than the 4, it also has to guaranteed be smaller than the 3, I think. Let's think about that. Does it? Maybe not. No, actually, maybe not. Maybe, what if it's like 1, 8? This is 7, 10. Yeah, so now we have a problem, right? And then here, so 1, 8, 7, 10, and then now, yeah, so now we do have a problem. So now let's say we actually do have like a 9 here and 11. So this wouldn't work because, yeah, this exact solution wouldn't work because this 7 wouldn't do anything because it's smaller. Now this 9 wouldn't do anything either, even though it can go over here. So I think I'm starting to see it again. And I think instead of a stack, what we actually, we don't care about like the stack. What we need is the smallest possible end. So instead of a stack here, I think we are actually going to want to use a heap. Yeah. Okay, and I think for a heap would be good. And so for a heap, let's go through that implementation of this example. So let's say we have a min heap, and we do the same thing. So we take whatever the min end is, and we say, is our interval bigger than that? And because our intervals are sorted, we are going to always get like the first one we can, I believe. Yeah, I think that makes sense because because start has to be smaller than end. So if start is smaller than end, then or equal to the end, then like when we have this value, the value after it is going to be guaranteed to be the smallest possible value, I think, because these are sorted. Okay, so our algorithm is going to add. So what our algorithm is going to do is if there's something in the heap, whatever the min value is, if that value is smaller than what we're currently pushing in, then we're going to update its res to be like the j. So let's just go through that. So at first we're going to add 8.2 into the heap, and remember this is going to be a min heap, and it's going to be sorted by this first value, which will be the end value of the. So it'll be this right here. Okay, so we add 8.2. Now we try 7.10, and we just say while the 7 is greater than or equal to heap 0, which would be this value, get rid of it, but it's not. So then we add it in. So 7. So we need to add the end. That's this. Now we have this 9.11. And same thing. So while 9 is greater than heap 0, so it actually is here. In which case, we would say at index 2, we would make that 9. And then the last start value should never have a j. So if you look at it like this, the only way the last start value has a j is if it's something like 9.9. Because then the j value for it would be itself. Okay. So I think that's what we're going to do for algorithm. So instead of this stack, we don't want a stack, we want a heap. And now I think we got it. So let's do that. And let's just say for interval in intervals. Yeah. While heap and. So instead of interval, let's just use start end. Because we want the start and the end value. So while. Actually, we want the index as well. So we want a lot of things. So I think we want for IV in enumerate intervals. And then start end equals v. We could probably do something like that here, but whatever. Okay. So now what we need to say is while heap and end is greater than or equal to heap 0. That means we have a valid. We do have a valid j. Then we're going to want to pop from the heap. So say what we really want is we just want the we don't really care about the start value, we just care about the index. So it's just going to be like this, index equals heap pop heap. Yeah, because you're going to have the end value here and then the index, and you don't really care about what this is. So if you want a value you don't care about, this is the syntax. Now we just do res index equals end. Okay, so now that we did that, now we need to do one more thing, and we need to say if start equals end, then the j for that is itself. So if start equals end res. Oh, actually, so this is not start end v. This is start end index. Let's just say we already used that, so let's just use something else. Let's just say temp, whatever. Okay, so because this v, this interval is actually gonna, remember we added the index into the interval, so it's start end index. Okay. Anyway, so then, yeah, actually, so we don't actually need. Yeah, I was gonna say we don't actually need the index in intervals, so this is actually not needed. So this can be interval because the intervals are already sorted, and so we actually do have it saved here. So, right, because we sorted the intervals, so the index is not what we care about. Like, this is the actual index, not that index. Okay, so if start equals end, that means that the res of temp equals end. Yeah. Because like I said, if you have something like 9, 9, then the smallest value greater than or equal to 9 is going to be 9. Okay. And then otherwise, we need to push it onto the heap. So heap push heap. What are we time? 20? Okay, it's not bad. I think if you get it roughly 25, 30, this is definitely not the easiest problem, I think. So okay, so heap push heap. And then we need to push the end and the temp. We don't care about the start. Okay, now we just return res. Okay, let's hopefully just go over real quick and see. So we sort the intervals, good. Then we have our output. We have a heap for interval. We get the start, we get the end, and we get the index. While heap and end is greater than or equal to heap 0, makes sense. As soon as we added something new, we keep trying all the, yep, makes sense. Index equals heap pop heap, res index equals end. Okay, good. If start equals end, res temp equals end. I think that's correct. Else we push onto the heap. Okay, looks good. Let's try this. Okay, expected 3 got 1. Ooh. Okay. End is good. Oh, I see. So this is not heap 0. This is heap 0. We need the actual start value, which is 0. Okay. Then let's take a look. What we got? Okay. Oh, are these indices that we need or something? So let's see. So there is no right interval. Okay. The right oh, so we need the index instead of the value is what we screwed up at. Right? So for 1, 4, there's nothing. For 2, 3, yeah, we need the index. Okay, so that's what we screwed up. So let's fix that. So res index equals temp, I believe. Res temp equals temp. Let's see. Okay, let's see what we got here. So case 3, we got 2, 2, 1. Does there have to be a unique J or something? Oh, let's see. So we got 2, 2, 1. 1, 4 would be this. 1, 4. 3, 4. I see. Okay, let's just print the intervals just real quick. Just to make sure it's correct. It should be. Okay, so 1, 4, 0, 2, 3, 1. Yep, that's fine. Okay, so let's think about this. What are we at? We're at 23 minutes, so let's try to finish this. Okay, so res equals -1 times length. That's fine. That's fine. Start, end, temp. Yep. While heap and end. Ooh. Ooh. Do we have a problem here? I think we do. Yeah. So this should not be start. This should be start. Because this is the end. So the start should be greater than or equal. Yeah. Okay. Perfect. Okay, cool. So definitely could have done better, but, you know, got a solution. Think optimal solution. We'll take a look at the editorial, but... So let's look at the time here. So we are sorting, so it's already on log n. For most of these interval problems, you have to sort because the order matters, so that's whatever. So we have... Yeah, we can have max and heap pushes and heap pops, but we already have an n log n here. That's the other thing. If we need a heap, sorting is fine. It doesn't take anything away. Yeah, so I think n log n for that. Space. So we have a heap, and the most items it can technically hold is n. So that's big O of n. We have res, but that's going to be n as well. So I think that's it. let's take a look at the editorial real quick to see how we did. Brute force, no good. Hash map, n squared, did better than that. Sorting, binary search, n log n, cool. Space, n res. Yeah, so technically, yeah, if we, okay, tree map, n log n, 2 arrays, binary search, n log n. Oh yeah. So, and they're asking, why is there no heap approach? And that's what we did. So we got the optimal time and space complexity, so that's good. So I'm happy with that, and we got it in 25 minutes. And we did have a few bugs, but they weren't like a right. So what were our bugs? We had one wrong variable here, and then we had some other wrong variable, but our actual implementation was right. We just had like a wrong variable name, so I'm pretty happy with that, I think. Now, what I will say we can improve is definitely don't want to be printing like the intervals array, because yeah, probably in an actual interview, it's not going to be the best to like print a bunch of stuff. But yeah, as far as that, we finished in around 25 minutes, and we got the optimal solution with a little few variable name hiccups here and there, but I'm pretty happy with it. So that's all for this one, and if you like this kind of problem, then please like and subscribe, and I'll see you in the next one.